Hi, I'm Colton Sundstrom, and this is our Applied Cryptography semester project.
And I'm Christopher Leung. And we will be talking a little bit about the component diagram here today. Some of the interfaces that we have used and frameworks include a Flask application server in conjunction with the HTML to mimic kind of like the capabilities of a front end web server. This framework makes great use of built-in Python packages, as well as the JSON web tokens for user authentication, as well as a SQL Alchemy library that is storing all of our users in a database. And of course, we will showcase in the later presentation, but all of our users within this database have been appended to the database with a unique ID, as well as their passwords are salted such that no user is sitting in plain, no user sensitive data is sitting in plain text. And the ability for the Flask front end to quickly render HTML files for the user interface to showcase back to either the patient or the auditor. Upon startup, you can see on the left-hand side, a user such as the client or the auditor is prompted to either sign up with a portal or login. And after the user has performed successful sign up, the user credentials are then used to log into the portal, as well as their credentials are stored within the SQL Alchemy database that again salts and hashes their password to mitigate their passwords being stolen in plain text if a adversary were to come across and query the database. Another use case would be a user successfully logs in, and our Flask goes ahead and renders either two database templates, either a user dashboard or a auditor dashboard. And these patient dashboards are allowed the user to basically create, delete, modify, print, copy, or query their own EHR data. Similarly, the auditor dashboard only allows for two commands, which is query all of the EHR data, all of the records that would be basically all the leaf nodes within our blockchain, as well as a specific user query for their EHR data. So our Flask application kind of sits in the middle between the intermediary between the client as well as the server, and they will be issuing commands through API calls that sits on the Flask side to be able to interact with our blockchain. And Colton will be talking about how those transactions are approved, as well as the inner workings of how we store data within our the EHR blockchain.
Yeah. So the audit data that we're kind of talking about we're building upon a blockchain. So using sequential hashing to prove the validity of what came before. And then for the actual EHR data, we're storing those in two layers of Merkle trees. So the bottom layer of the Merkle tree is the user ledger, which so you can see here, a user ledger with A, B, and C, and then going to add a fourth item to the ledger. We'll change the root node, and then the upper audit Merkle tree, the audit tree that we call, is a Merkle tree built upon each of the user roots within our system. So any update of any user will yield a different root, and then for a valid command, that root of the upper tree is what we use as our current data within our blockchain, and then that hashed with the previous block's hash creates the new current hash of the blockchain. So it's append only, and also resilient to changing previous data because otherwise the latest hash will not align. So a little bit about the node network on the back end. So that first slide that Chris was talking to kind of showed the front end, the application, and then the back end where there is our node servers. So the nodes are independent, decentralized nodes. Each one runs separately of each other, and each node gets a singular vote within the voting system that we call the consensus or the quorum. So any addition to our blockchain, to our audit data, is fielded through a single node. So the Flask application has a audit server. So the audit server fields requests to the nodes, and then audit nodes, kind of the terminology we use to explain the two different styles of nodes in our system. The server sends over a request to one of the nodes currently active in the system. That node generates the latest hash based off what that new data would be, and then shares that along with the Merkle proof for that user tree to make sure that it is append only out to each of the other nodes. And then the other nodes compare that to their current state, and then verify that if added to their audit data, that the resultant hash matches to what the other node is advertising. And then if so, they return a vote of true back to the original node. And if that node reaches a threshold, which is configurable within the system, then that node is able to add that to the blockchain. And then each node would have added it to their own blockchain. And doing this allows us to achieve the decentralization goal of the project, in that any malicious node, so a compromised node, can't overpower the will of the true and remaining nodes. So as long as there are more accurate and honest nodes within the network, then this scheme will hold. So a little bit about how the nodes find each other. So each node is on a peer-to-peer network between all of the other nodes, and when they come up, they publish to a multicast topic within the system to advertise their current name and then their ports to communicate on, as well as their IP. Everything currently that you're going to see is going to be running a local host, but could be configured to run over a network. And so each node, having listened and hearing a new node that is not currently in their ledger, they will add that to their ledger, go and reach out and make a active connection with the other nodes. Additionally, any requests coming in from the server to one of the nodes is encrypted. So all of the data in transit is protected, as well as all of the records stored on the node at the time of close will also be encrypted, and encrypted additionally with HMAC. So any changes we're able to achieve authenticated encryption of the data within the system. And then a little bit on the timing diagram on the top here kind of shows each node on a 5-second window will publish that they're awake. And then as long as a node comes up within 5 seconds, each one will know all of the other nodes on the system, and then they're able to kind of self-heal through that system. Okay.
Awesome. Now we're going to transition away and actually perform a live demo with kind of the user interface and what a patient/auditor would witness. So Colton is going to spin up his 2 nodes, audit nodes, which will be keeping track of all of the current state of the Merkle tree, and he will also have a front end Flask/HTML web server interface that the user would see.
Okay, so you can kind of see right here the nodes having woken up, they publish their current status, as well as this is kind of the nodes finding each other. So it sees, so this top one sees that node A is publishing on 9876 and 9875, and node B is publishing on 9871 and 9870, as well as the audit server, which is our back end Flask communicator, is publishing on just the server port of 9890. So then we can go to the front end.
And just while he brings it up, this audit server is the only single point of entry that our Flask web portal would be able to communicate with our backend. And as you can see, right now it's on localhost, but of course this could be extrapolated to being hosted on a web server. But if we take a look very quickly, two actions here, we have a patient login, we have a new patient setup, and let's go ahead and take a look at the login page. So we have a like login for a EHR patient, basically, and we have a login credential of patient1 at usc.edu with the password. And our Flask will go ahead and take all of those form entries and perform error checking, as well as create a new EHR event that the user logged in at a certain time.
So we can see on this side that the top node here received a request from server A, which was the Flask. This is the encrypted payload. After decrypting that, it sees that it wants to add this to a ledger, and then it communicates that over to node B, the other node, having received the proof, and the new node responds in the affirmative, and the record is added to both of them.
Awesome. Let's go ahead and do a very simple test and perform all the user buttons really quick. So let's go ahead and create a EHR data. So this would be like a comment that let's just say a user were to submit to his doctor, for example, and then this would create a EHR record. And you can see at the bottom that it connected to one of the nodes. And we would be able to kind of see that that has been appended to the user data. Let's go ahead and click delete EHR data. So that will send a request to the backend saying, hey, we would like to perform a deletion, but of course, this is since the nature of the Merkle tree is append only, but it does record that within our user. Let's go ahead and do a modify. So if a user wanted to redact or modify a comment, that would be captured as well. Let's do a query. So then our query would actually show a user login, a user create, a user delete, and a user modify. And we can see that the user was created earlier. They logged in, created EHR, deleted, and changed a couple events. And this is part of their EHR audit log. Let's go ahead and do a print. So the user goes ahead and says, hey, I want to print something out. And then let's do the last command, which is the copy. So they wanted to copy an entry, for example. Of course, this is a prototype, extended prototype, and we would pass this on to some of the implementers. And let's do a final query to showcase that we appended a couple of new entries to our EHR record. So as you can see, it's pulling all of the data from this user, and the user ID 975195 has done all of these things within the allotted time frame. And that is being handled by our blockchain on the back end. Let's do a logout, which will also send a append to their user record that they have logged out of a session. And let's go ahead and showcase very quickly the number of entries that a user has for their record, right?
Okay. Yep. So we can see, as we started, this was at 1 for the create, 2 for the login, and then each of the subsequent records and the queries. So now that user shows 12, and we can see kind of both systems align on that, and both share the same root, and we can see the 9 additions to our blockchain. And then the other thing to note is the server, when it is deciding which node to speak to, randomizes between the current nodes. So you'll see as we issue commands from the front end, the different servers will respond to the request based off a random input, so that you can't force a malicious connection between a server and a node. It's randomly generated. So even if you controlled some nodes within the system, you still have to beat a random element of which node will field that request.
Awesome. And Colton, do you mind really quickly capturing that user ID if we will be needing it for our next demonstration?
Yeah, 975195. 975-195. Okay.
Okay, and then we will go ahead and showcase an auditor, one of the three auditors. So they actually have a very specific domain, which is audit.usc.edu. So no user can sign up with this particular domain. And once you click login, as you know, kind of similar to the patients, they append a login record for the auditors as well. And you can see that the admin dashboard here is a little bit different. So the auditors would be able to query all of the EHR record data for every user, as well as query a particular user based off of their unique ID, which is also a primary key within our database. So if we go ahead and query EHR data for that particular user that we patient one, I believe it was, we will go ahead and capture all of the things that were recorded back from when the user was created all the way up until they logged out. And of course, right now, you do not see it, but it also has created a new entry called admin user query or something like that, and it has appended to their EHR record. So if we go ahead and redo that again with the same user, we can see that the previous query that we performed has been appended to their EHR audit log. And right there, admin user query. Let's go ahead and showcase really quickly the query all EHR data. And currently we have 10 patients and 3 auditors. So all 10 patients will show up. And of course, this will can extrapolate to n number of users. But as you can see, that original user that we created for patient one has a much larger audit record than everybody else. And you do see that admin user query the second time to showcase that we did perform a query on those on that user twice. Everybody else is kind of we've instantiated and populated their user account, but haven't monkeyed around with it a little bit. Okay, and looks good. Let's go ahead and log in as the patient just to verify that we do see that those 2 admin queries on that side. So patient one at usc.edu. Awesome. Okay. And then we'll go ahead and query the EHR data. And we can see that
Loading. Not sure what happened on that one. Oh, there it goes.
oh,
Oh,
overloaded. Mind if we
right.
just restart it really quick?
Yeah, we can restart that front end.
Sorry about that, everybody.
It's totally fine. So we'll close the app. Save these. Oh, this work successful. Okay. It actually gives us a great opportunity to showcase the import-export. So you can currently see current state of the system. So we will stop the 2 backend servers. So we have a fresh connections to that front end. Okay, and we can restart the servers. And with all of those records that we had, they are repopulated. So we see all those 16 records for that that first user. And let's start the front end application, so which will connect to HTTP. Okay,
awesome.
Patient one at usc.edu. So we go for a login.
Prove, and then give it a couple. So it did print out 16, right?
Yep, now we're at 17.
17. Okay,
So
awesome.
we captured that login.
Okay. And let's go ahead and query one last time. And you can see that there will be actually 2 login attempts without a logout, but yep.
There it goes. Yep, there it is.
Yep. So we do have those 2 admin user queries. We have a login and then a query, and then unfortunately it got
disconnect.
hung, and then we logged in again, and the last entry on that one would be a query. But that showcases all of the functionality for a good use case, and we kind of wanted to go through a couple captures of failed logins.
Just close those down. I think that hang up caused some more issues. Okay, but
That's fine, but we
unless
can
we still
show
showcase the front.
So let's go ahead and utilize a valid email address and a wrong password, for example.
Okay, valid email. So that same patient.
Yep.
patient1@usc.edu.
And then their password totally bogus. When they click on login,
Oh.
of course, the Flask will query the database and say, hey, is this is not valid. Let's go ahead and try doing a incorrect user and a valid password, for example, right? So if we just change that to something like 12 or whatever, that's not yep. And then it will try to find that patient within the Flask, and that is not in the database. Let's go ahead and do a user create. And a couple things here. So let's do a valid user with a mismatched password.
Okay.
So like John Doe at usc.edu. And then valid mismatched password.
Okay.
Okay, and you get a password mismatch. And also let's do a auditor, trying to assign a auditor to John Doe. So if we have a audit.usc.edu with a valid password, it will give out a error such that we're not able to create this user account because it's a admin. They're not authenticated, and this is just a simple patient, for example, and you were not able to accept that. And then another.
So we can do a successful John Doe.
Yes, and we
add that
actually need to
the-
spin up the server again.
Let me get one of them online. Just a moment. If you want to talk a little bit about the database while I get this.
Yep. So how the database works on our end is the Flask will go ahead and capture, of course, the plain text password upon user creation, and also capture the user password during login. However, the Flask server does not store those user passwords in plain text when you query the database, and we will be showing that to you very shortly. The passwords are actually salted first and then hashed and then stored. The calculate hash is going to be compared during the login phase, right? So if we go ahead and
Submit.
sign up, yes, with the valid password, valid email, and does the node pick that up?
Oh, the
Plus,
backend did not want to see that node. Let me take that down. I'll have to restart the backend since I had to restart the servers.
okay, no
So
worries.
put the class back up.
Let's try with a different email.
Okay.
Yes. So go ahead and do like
Johnson. S.
And
Johnson.
make sure you have the server running as well, please.
Yep. Let's good call. Okay. Yep. And I see on the back end that the server was able to find it.
Yep. All right. Looks good. Have a valid user and clicking sign up, they will create that user account. Mismatch.
Oh, I must have fingered. Steve Johnson, S. Johnson, usc.edu, and sign up.
Awesome.
Okay, so
now
we can see it
that
added there.
added to the database, as well as a user blockchain. And then if we go ahead and log in with the same user credentials as Johnson, usc.edu, and the last one, they will have a login and a creation entry in reverse order. So you have a user, and now it's grabbing all of the queries, and of course we have that user and login. And that's a good time to kind of showcase, I believe now is the database, right?
Yep.
So in our database, we go ahead and select everybody, and we have an addition of 2 members within our database. So we have John Doe, as mentioned before, and we also have Steve Johnson, and you can see on the 4th column right there, the password salt is going to be appended to the password and is hashed, and only the password hashes are going to be compared upon logging in. So each user has a unique password salt that, of course, when they're comparing it, if the salt does, if the password hash does not match, then of course the user gets that error code and says, unable to log in. So I believe that's it, right?
That concludes our system. Thanks.
Thank you.